Welcome to today's lesson. Today we are going to learn the structural design of rigid pavement. For rigid pavement on concrete pavement, it normally has a concrete base, a subbase, and a subgrade underneath. In the previous two lectures, we have learned the structural design of flexible pavement. Now let's focus on the structural design of rigid pavement or concrete pavement. Concrete pavements may be used in all urban classes of road pavement and moderate to heavily trafficked rural road pavement. There are mainly four principal types of concrete pavements: plain or jointed and reinforced concrete pavements, PCP; jointed reinforced concrete pavements, JRCP; continuously reinforced concrete pavements, CRCP; and steel fiber reinforced concrete pavements, SFCP. There is also another type of concrete pavement, the pre-stressed concrete pavement, but we are not going to discuss its design procedure in this lecture. Now let's look at the details of each type of above four concrete pavements. As shown in the graphs are the top view and side view of the plain, jointed and reinforced concrete pavement, PCP. In plain concrete pavement, reinforcement is sometimes necessary to control cracking. The slabs are normally 4.5 meters long with doweled square joints. The dowel bars are placed at the transverse joint of concrete pavement, and they take part in partial wheel load transfer from one slab to its adjacent slabs. The dowel bars allow actual thermal expansion and contraction of the concrete slab along the axis of the dowel. Slabs are reinforced if it is anticipated that cracks could occur due to stress concentrations, which can't be avoided by rearrangement of the slab joining pattern. The plain concrete pavement have to be reinforced in discrete areas, such as odd-shaped and mismatched slabs and in base anchor slabs. Also, typical spacing between transverse joint is 3.7 to 6.1 meter, as shown in the figure. In the longitudinal direction, the tie bar is normally used. They are the connectors used for holding faces of rigid slabs in contact to maintain aggregate interlock. Unlike dowel bars, tie bars do not transfer the load, so that's the major difference between them. The jointed reinforced concrete pavement is normally mesh reinforced with doweled joints spaced between 8 and 12 meters and up to 15 meters, as shown here. The transverse joints are perpendicular to the direction of travel. Intermediate cracks are expected to form at about 4 to 6 meter spacing and often within days of paving. In JRCP, the purpose of reinforcing steel or reinforcing mesh is not to prevent cracking of the concrete, but to hold tightly closed any cracks that occur in such manner that the load capacity of the base is preserved. If suitable reinforcement is provided in a slab of acceptable proportions, cracks should not require any treatment during the pavement design life. Compared with the JRCP, the CRCP is an integral cast. It does not have dowels and tie bars, so more cracks are generated. For CRCP, sufficient continuous longitudinal steel reinforcement is provided to induce the desired transverse cracking at random spacings of about 0.2 to 2.5 meter, and then hold these cracks tight. So no need the contraction joints. The contraction joint is a transverse joint to control cracking due to pavement contraction caused by shrinkage and temperature fluctuations. The left figure is the side view, and right figures are the top and side view. The transverse reinforcement is provided to support the longitudinal steel. Transverse steel also provides insurance in the event of unplanned longitudinal cracking. This is a great way to make a pavement really strong and capable to support tremendous loads. It's also very expensive, and when the day comes, when the pavement has to be demolished, it makes for a nightmare for the demolition crew as the steel continues to perform its job of holding the concrete together. The last one is the steel fiber concrete pavement, SFCP. Steel fibers are typically between 15 millimeter and 50 millimeter in length, with either enlarged ends that act as anchorages and or crimping to improve bond. Typically, fibers are added to the concrete at a rate of approximately 45 to 65 kilograms per cubic meter. It provides improved resistance to cracking, and it is ideal to areas with a high percentage of irregular slabs. Because of the increased flexibility in the design of the joint layout, such type of concrete pavement is the only option for intersections and roundabouts. This type of pavement is also often used for toll plazas and bus stops. Now let's look at the concrete shoulders. It provides a lateral support to the main slab of pavement and also results in additional stiffness. The concrete shoulders improve the pavement performance and enable a lesser base thickness to be adopted. The concrete shoulder must be either integral or structurally tight to satisfy the width shoulder criteria. Substantial curves such as urban curve and channel can be considered to provide with shoulder support, provided that they are constructed of structural grade concrete of strength consistent with the pavement, and they are effectively tied to the pavement, and the joint has a corrugated face for load transfer. In terms of subbase or rigid pavement, House rules recommends lean concrete subbase or bond subbases. A bond subbase is composed of either cement stabilized crushed rock with no less than 5% by mass cementitious content. This is to meet erosion resistance requirement. Other types of bond subbase are dense graded asphalt or rolled lean concrete with characteristic 28-day strength of equal to or greater than 5 megapascal. Once we have the design traffic entity, the selection of the minimum subbase type is determined from table 9.1. According to different calculated NDT, we choose different type of subbase from this table. Within the table, the LCX stands for the lean concrete subbase. So if the design traffic is greater than 1 to the power of 1 times 10 to the power of 7, and for continuously reinforced concrete pavement, CRCP. A heavily bound subbase with an asphalt surface is deemed as an acceptable alternative to LCS. Now let's see the factors in thickness determination. Similar as that for flexible pavement, for rigid pavement thickness design, the strength of the subgrade is also assessed in terms of CBR. All materials within 1 meter below the subbase must be evaluated to determine the design subgrade CBR. It is also required that the selected subgrade material ought to be consist of a uniform, volumetric, stable material that is constant for the service life of the pavement. The corresponding CBR has to be at least 5%. Another factor for thickness determination is equivalent subgrade strength. For 1 meter underneath the subbase, the subgrade design CBR must be determined based on a multi-layered subgrade system. The equation 25 could be used to determine the equivalent subgrade strength CBRE based on the strength of the supporting soil, where the CBRI is the CBR value of the S layer. HI is the thickness of the S layer, and EHI is equivalent to a depth of 1 meter. There are some conditions to follow when using this equation. The layer with thickness of less than 200 millimeter must be combined with an adjacent layer, and the lower CBR value must be adopted for the combined layer. It is also assumed that higher CBR materials will be used in the upper layers. The formula is not applicable where weaker layers with smaller CBR are located in the upper layer. In other words, the magnitude in terms of CBR has to be in descending order. If there's any filter layer, then it must not be included in the calculation. Finally, the maximum CBR for the use of this formula is 15%. So that's for the 4 conditions we have to follow when using this formula. Now let's look at one example. We need to determine the equivalent CBR of the stratified subgrade as shown in the diagram below. Firstly, because the layer thickness of the top 2 layers are less than 200 millimeter, you see the first layer and the second layer, both less than 200 millimeter. So we need to combine them to form 1 layer, and the lower CBR value is used for the new layer. So that's the new layer thickness. That's the corresponding CBR. After this, all the previous conditions of equation 25 are met. The equivalent subgrade design strength CBRE could be calculated using equation 25. And after we plug in all the values into this formula, we get the CBRE of 4.7. The effective subgrade strength also influences the thickness determination. So the composite strength of the subgrade and the embedment soil below it is termed the effective subgrade strength. So previous research and experience has indicated there's an increase in effective subgrade strength with the use of bond and lean concrete subbase. The red figure, the figure 9.1, could be used to determine the effective subgrade strength using the base thickness design. We will talk more about this figure in the later part of this lecture. But now The factor in thickness determination is base concrete strength. Normally, the 28-day characteristic flexural strength of the concrete is used as the design strength. Also, we have the requirement that the minimum characteristic design concrete flexural strength with design traffic of 10 to the power of 6 HVAG or more is 4.5 megapascal at 28 days. And for steel fiber reinforced concrete pavement, it is 5.5 megapascal. We know that for concrete base, normally it needs long curing time to gain the strength. But tracking paving construction technique is a viable option for new and rehabilitation pavement construction. This is because it allows traffic to resume on the concrete within 24 hours of paving. The final factor is the project reliability. During design, the actual group loads are multiplied by a load safety factor, LSF, or specified rigid pavement type. For PCP and DOT and CRCP, here the DOT mainly represent the joint reinforced concrete pavement, JRCP. The LSF can be taken from the table according to the project design reliability in between 80% and 97.5%. The load safety factor provides a certain degree of conservatism by allowing for the possibility of unpredicted heavy truck loads and a higher level of pavement serviceability. For flexible pavement, we consider 3 distress modes: the fatigue damage to asphalt, fatigue damage to cemented material, and subgrade rotting and loss of surface shape. To determine the thickness of rigid pavement, we followed the Portland Cement Association method from USA. It is an old method, but still commonly used in modern days. For the base thickness design of the rigid pavement, 2 distress modes were considered: the flexural fatigue cracking of the pavement base and subgrade or subbase erosion from repeated deflections and joints and planned cracks. For flexible pavement mechanistic design, we have to follow 18 steps, where for rigid pavement design, we need to follow 19 steps. Firstly, we have to select a pavement type, then decide whether tied or integrally cast concrete shoulders are to be provided. Next is to determine the subbase thickness and type of and effective subgrade strength. Afterwards, we need to select the 28-day characteristic flexural strength of the concrete base, FCR, and then select the desired project reliability and the load safety factor. Step 7 is to select a trial base thickness. Then we calculate the expected load repetitions of each actual group load of each actual group type. From the traffic load distribution, we find the highest actual load for the SASD actual group and determine the allowable repetitions in terms of fatigue. Then we calculate the ratio of the expected fatigue repetitions to the allowable repetitions and determine the percentage of fatigue by multiplying 100. We also need to work out the allowable number of repetitions for erosion for the highest actual load for the SASD actual group. Again, calculate the ratio of the expected erosion repetitions to the allowable repetitions and find the percentage of erosion damage by multiplying 100. Step 9 to 12 will be repeated for each actual group load up to a load level where the allowable load repetitions exceed 10. Afterwards, we sum the percentage of fatigue for all relevant loads of this actual group and the percentage of erosion for all relevant loads of this actual group. Step 9 to 14 will be repeated for actual group type. Step 16 is to sum the total fatigue and erosion damage for all actual group types. Then steps 9 to 16 are repeated until the least thickness that has both total fatigue and total erosion damage less than or equal to 100% is determined. That thickness will be the design base thickness. We also need to meet the minimum base thickness requirement from table 9.7. Lastly, we confirm the final design base thickness and consider the potential application of additional thickness tolerance. So in short, a trial design base thickness is selected and the total fatigue and erosion damage is calculated for the entire traffic volume and composition during the design period. So if either fatigue or erosion damage exceeds 100%, then the trial thickness is increased and the design process is repeated. The design thickness is the least trial thickness, which has a total fatigue less than or equal 100% and a total erosion damage less than or equal to 100%. Now let's look at example 2 of base thickness design. We are required to design the base thickness for the pavement with the following given conditions. The characteristic 28-day flexural strength of the concrete is 4.5 megapascal. The desired project reliability is 95%. The subgrade design CBR is 5%. The design traffic for 40 years design life is 4 times 10 to the power 7 HVAG. We have the traffic load distribution data as well. Step 1 is to select a rigid pavement type. So it's either PCP, JRCP, CRCP, or SFCP. For this example, we selected PCP, the plain concrete pavement. Step 2 is to decide whether concrete shoulders, either tied or integrally cast, is to be provided. A concrete shoulder is considered in this case. Step 3 is to determine the type and thickness of the saw base. As the design traffic is 4 times 10 to the power of 7 HVAG, so that's greater than the last category, the value in the last category. So from table 9.1, 150 millimeter lean concrete saw base LCS is selected. Step 4 is to determine the effective subgrade strength. From figure 9.1, for 150 millimeter LCS and subgrade design CBR of 5%. So that's 5%, that's 150 LCS. So we found the effective subgrade design CBR equal to 75%. Step 5 is to select the concrete 28-day characteristic flexural strength FCR, which is given in the question as 4.5 megapascal. This also meets the requirement of minimum characteristic design concrete flexural strength. Step 6 is to select the desired project reliability and load safety factor as SF. As the project reliability is given as 95%, and we chose PCP. From table 9.2, we found a load safety factor as SF of 1.3 for the rigid pavement design. Step 7 is to select a trial base thickness from table 9.7. So the minimum thickness for PCP and design traffic of 4 times 10 to the power of 7 actually AG is 200 millimeter. We have another way to determine the base thickness. So figure 9.2 is the design chart for concrete base thickness. The chart allows designers to compare and design base thickness for different traffic volumes, effective subgrade strength, and safety factors. According to the NDT of 4 times 10 to the power of 7 and previous results, effective subgrade design, CBR of 75% and LSF of 1.3. This figure suggests a base thickness of approximately 210 millimeter, which is greater than 200 millimeter, the minimum thickness. So this value is adopted as a trial base thickness. The step 8 is to calculate the expected load repetitions. The NDT is 4 times 10 to the power of 7 HVAG. The traffic load distribution for SAST is shown in this table. So for each actual load, we could calculate the expected load repetitions for SAST group by multiplying the proportion of load by proportion of actual group by the design traffic. So the expected load repetitions are shown in the last column of this table. Next is step 9, which is to use equation 26 and 27 to calculate the allowable load repetitions in fatigue distress mode and F for the SAST actual group. The SR could be calculated using the below formula here, where the SE is the equivalent concrete stress in megapascal. So we will provide a bit more details in the next slide. The FCR is the design characteristic fluctual strength of concrete at 28 days. The capital P is the actual group load. LSF is the load safety factor. F1 is the load adjustment for fatigue according to actual group. It has a different value for different type of actual group. So for SAST, we just use the value of 9, and for QADG, we use the value of 72. This is the formula for SE. We are the A, B, C, D to J coefficients in table 9.4. The D is the concrete base thickness in millimeter, and EF is the effective subgrade design CBR in percent. So for this SAST case, we refer to the value for A to J in table 9.4 from the next slide. So we can just get the corresponding constant for the value from A to J. And EF is, the D, that's 210 millimeter, and EF, that's 75%. So we're able to just get the equivalent concrete stress SE as 0.751 megapascal. So this is the table 9.4. It contains the coefficients for calculating equivalent stress, equivalent concrete stress SE, both for with concrete shoulders and without concrete shoulders case. Because in the beginning, we determined to use the concrete shoulders. So we just pick up the values in the right hand side of this table. and for the SASD group. Step 10 is to calculate the ratio of the expected repetitions to the allowable fatigue repetitions and multiply 100 to obtain the fatigue damage. Step 11 is to calculate the allowable repetitions for erosion distress mode NE using the formula 29. In this formula, the physical meaning of P and L as F are same as before. As F2 is the adjustment for slab edge effects for value of with value of 0.06 for base and no concrete shoulder case, and 0.94 for base with concrete shoulder case. F3 is the erosion factor, which could also be calculated from equation 28. F4 is the adjustment for erosion due to different type of axial group ranging from SASD to QADT. The formula for erosion factor F3 is shown here, where the parameters A, B, C, D to J are coefficient in table 9.5 to 9.6. Again, the D is the concrete base thickness in millimeter, and EF is the effective subgrade design CBR in percentage. Equation 28 is used to calculate both SE and F3, which means the expressions are the same and only the coefficients are different. This table 9.4 and 9.5 contains the coefficients for calculating erosion factor F3 for undrailled bases, both for without concrete shoulders and with concrete shoulder cases. This table 9.6 lists the coefficients for calculating erosion factor F3 for DOT or CRCP base, again for categories of without and with concrete shoulders. If we divide the expected repetitions by the allowable erosion repetitions NE and multiply 100, we get the erosion damage in percentage. Step 13 is to repeat steps 9 to 12 for each load on this axial group. Next step is to calculate and sum the fatigue and erosion damages for each axial group. Step 15 is to repeat steps 9 to 14 for each axial group ranging from SADT to QADT. This table is the summary of the calculations for the axial group SASD. The first column is the actual group load P. The second column is the design load, which is P times L as F. The third column is expected load repetitions from step 8. The fourth column is the allowable repetition for fatigue distress, and the values comes from equation 26 or 27. The fifth column is the fatigue damage, which is calculated as the expected repetitions divided by the allowable repetitions and times 100. If we sum all the fatigue damage, we get the value of 124.69%. The sixth column is allowable repetitions for erosion distress, and the values come from erosion equation 29. Similarly, we could work out the erosion damage in the last column. The sum is around 6. The total percentage of fatigue damage and erosion damage are 124.69 and 5.98% for all relevant load in this axial group SASD. The previous slide is to run steps 9 to 14 to get the total damage for actual group SASD. This slide is to repeat steps 9 to 14 for TASD. The percentage of total fatigue and erosion damage are summed as 0.19% and 46.42% for this TASD actual group. Next is to run steps 9 to 14 for single axial dual tears SADT. The total percentage of fatigue and erosion damage are summed as 0.46% and 34.39% for actual group SADT. Similarly, for the data for actual group DADT is shown in this table, and the total percentage of fatigue and erosion damage are summed as 0% and 32.07%. The data for triaxial with dual tears TRDT is shown in this table. The total percentage of fatigue and erosion damage are 0 and 0.52% respectively. Finally, the data for QADT is shown in this table, and we can work out the total percentage of fatigue and erosion damage for this actual group accordingly. The total percentage of fatigue and erosion for all actual group types and group loadings are obtained after we sum all the corresponding values. So the total percentage of fatigue damage is 125%, and total percentage of erosion damage is 119%. From step 16, we can see that both fatigue and erosion damage were greater than 100%. So the trial design is deemed unacceptable. We have to increase the base thickness and to repeat steps 9 to 16 until both the total percentage of fatigue and erosion are less than 100%. Next, we slightly increase the trial base thickness as 215 millimeter and redo the calculation. The corresponding total percentage of fatigue damage is 66%, and the total percentage of erosion damage is 93%. Both percentages are less than 100%, so this base thickness is acceptable. Step 18 is to check the minimum base thickness requirements. The design base thickness is the maximum value of the calculated base thickness and the minimum base thickness from table 9.7. So based on previous calculation, the minimum acceptable base thickness for this rigid pavement design is 250 millimeter. The minimum base thickness from table 9.7 is 200 millimeter. So the maximum of both values is 215 millimeter, which is the final base thickness. Sometimes we need to consider to add additional thickness to the design base thickness to account for the following factors. If there are any limitations of paving equipment and marine systems, or future surface retexturing treatments such as diamond grading and or grooving may lead to possible losses of the base thickness. Or if the pavement has an asphalt surfacing, the base thickness may decrease due to future milling of the asphalt. Step 19 is the final conclusion. The final base thickness for construction is the sum of the design base thickness and any additional thickness for the project. Now I would like to talk a bit more about the joints. There are two basic types of stresses which may be present in a concrete pavement. The stresses induced by externally applied loads resulting from traffic using the pavement, and the stresses within the pavement resulting from contraction and expansion movements and differential moisture and temperature changes within the depths of the pavement. We know the rigid pavement thickness design is dominated by stress caused by externally applied traffic loading, while for the location and design of joints are dominated by the need to control stresses and strains induced by environmental changes within the pavement. The objectives of joint design are to develop a joining system which will control transverse and longitudinal cracking and provide adequate load transfer across joints. So the pavement will have adequate reading qualities over its service life. Joints normally should be selected to minimize the intrusion of water and incompressible solids. This figure illustrates various joint types. The common joints are longitudinal joints and transverse joints. The purpose of longitudinal joints is to control longitudinal cracking by enabling hinge release of occurring stresses. The joints are tight wherever possible to keep them firmly closed. The transverse joints include the contraction joints, construction joints, and expansion joints. The contraction joints or control joint is mainly used to control cracking. These joints do not go all the way through the thickness of the slab, but rather about a quarter of the depth or length. They serve only as a weak place in the concrete where cracks can occur and then later be sealed up. Normally, these joints do not require a load transfer device, as it can be achieved by the interlocking of aggregates. Some projects also use dowel bars to fully bond in concrete. When there are multiple concrete pavements, a construction joint is typically used. Transverse construction joints are required for planned interruptions, such as at the end of each day's operations, at block out for bridges and intersections, or for unexpected delays when the suspension of operations is likely to create a joint. Construction joints are usually spaced to line up with contraction or control joint, so they are usually not a visible component after construction. Concrete is far more capable of resisting compressive stresses than tensile stresses. An expansion joint allows the concrete or steel to expand or contract within the change in daily temperature. At the discontinuities in the pavement, some allowance has to be made for potentially high compressive forces by providing expansion or acceleration joints. So expansion joint is mainly dot, and acceleration is mainly dot. A joint layout should be designed which is compatible with the road geometry, the length of slab, the type of joint, and the construction method. Advice on joint design and layout can be found in Road Traffic Authority (RTA) standard concrete pavement drawings, as shown in the bottom. A summary of rigid pavement design. We have learned the main types of rigid pavements: the PCP, JRCP, CRCP, and SFCP. The methods to determine the minimum thickness of rigid pavement subbase, the calculation of equivalent subgrade strength CBRE from layered CBR, the rigid pavement design including calculation of expected repetitions, allowable repetitions in fatigue NF and erosion NE. The calculation of fatigue damage and erosion damage. The total percentage of fatigue and erosion damages from different actual loading and actual group types. Accordingly, conclusions could be drawn on whether the trial design is acceptable. If not, we need to increase the base thickness until both total percentages of fatigue and erosion are less than 100%. Finally, we have discussed the joint types and functions. That's all for this lecture. I appreciate your attention and look forward to seeing you in the next lecture. Thank you.